Greetings everyone. I am Shangareshwari from 3rd B.Sc. Mathematics aided. I am here to present about Taylor's series. Now, first let us see about the theorem. The statement is, let f of s z be analytic in a region D containing z0. Then f of z can be represented as a power series in z minus z0 given by f of z equal to f of z0 plus f dash of z0 divided by 1 factorial into z minus z0 plus f double dash of z0 divided by 2 factorial into z minus z0 the whole square plus etc. and the plus f of n plus n factorial into z minus z0 power n. This expansion is valid in the largest open disk with center z0 contained in D. Now let us see the proof one by one. Now let us consider a circle. In that circle, let r greater than 0 be such that the disk will be the modulus of disk z minus z0 is less than r. The disk is contained in D. So now let us take an r1 which is 0 less than r1 less than r. So the circle, let us name the circle as C1. So let C1 be the circle such that modulus z minus z0 equal to r. We know that Cauchy's integral formula that f of z equal to 1 by 2 pi I integral of f of s divided by s minus s dz. Let us name that equation as first equation. And we know the same that also by the theorem on higher derivatives we know fn of z equal to n factorial divided by 2 pi I integral of f of s ds divided by s minus z the power n plus 1. Let us name this equation as number 2. Now let us consider only 1 by s minus z. So what we need to do, 1 by let us add and subtract z0. So we will get 1 by s minus z0 minus of z minus z0. So taking z minus z0 s minus z0 as common, we will get 1 by s minus z0 into 1 minus z minus z0 divided by s minus z0. So we know the formula that 1 by 1 minus alpha equal to 1 minus alpha the whole inverse. The formula is 1 plus alpha square plus etc. plus alpha power n divided by 1 minus alpha. With that formula we get the below equation. So now we know that with this equation we will get 1 by s minus z0 plus z minus z0 by s minus z0 the whole square plus etc. plus z minus z0 power n minus 1 divided by s minus z0 power n plus z minus z0 power n divided by s minus z0 power n into s minus z. Now let us multiply the equation throughout by f of s divided by 2 pi I and integrating over C1 using the equation we name it as 1 and 2. Now with that equation we will get f of z equal to f of z0 plus f dash of z0 into z minus z0 plus f double dash of z0 divided by 2 factorial into z minus z0 the whole square plus etc. plus f of n minus 1 into z0 divided by n minus 1 factorial into z minus z0 power n minus 1 plus rn plus etc. Now let us name it as rn equal to z minus z0 power n divided by 2 pi I integral of f of s ds divided by s minus z into s minus z0 power n. Let us keep this equation as rn. So next here s lies on the circle C1 and z lies on the interior of the circle. So that we will get that modulus s minus z0 equal to r1 and so that we will also get modulus z minus z0 is less than r1. So from this equation we will get the modulus s minus z equal to modulus s minus z0 minus z minus z0 so that we add z0 and subtract z0. So we will get greater than or equal to modulus s minus z0 minus modulus of z minus z0. We know that s minus z0 equal to r1. So let us substitute that equal to r1 minus z minus z0. So we will get 1 by modulus of s minus z0 is less than or equal to 1 by r1 minus modulus of z minus z0. Let m denote the maximum value of modulus f of z on C1. We take a value m so that we will substitute in rn, that is modulus rn is less than or equal to modulus z minus z0 power n divided by 2 pi into m into 2 pi r1 divided by r1 minus modulus z minus z0 by into r1 power n. So that we will get by factorizing we will get m into modulus z minus z naught divided by r1 minus z minus z naught into z modulus z minus z naught divided by r1 into n minus 1. Also we get that modulus z minus z naught divided by r1 is less than 1. So that while we are applying limit to Rn, so we know that Rn is Rn equation we named as Rn. So that by taking limit n tends to infinity, we get Rn equal to 0. So in that third equation, by taking the limit n tends to infinity, we get the Taylor series expansion. That is f of z equal to f of z naught plus f dash of z naught divided by 1 factorial into z minus z naught plus f double dash of z naught divided by 2 factorial into z minus z naught the whole square plus etc. plus f of n divided by n factorial into z minus z naught the whole power n plus etc. Now let us see the problems on regarding to Taylor series. So first problem is expand cos z into a Taylor series about a point z equal to pi by 2 and determine the region of convergence. So now we need to expand the cos z. So let us take f of z at cos z. So and another thing is given in the question, that is the point, about the point z equal to pi by 2. So the Taylor series for f of z about z equal to pi by 2 is, we need to substitute the z equal to pi by 2 in the Taylor series expansion. So that f of z equal to f of pi by 2 plus z minus pi by 2 divided by 1 factorial into f dash of pi by 2 plus z minus pi by 2 the whole square divided by 2 factorial into f double dash of pi by 2 plus z minus pi by 2 the whole cube divided by 3 factorial into f 4 dash of pi by 2 plus etc. So now what is our f of z? Cos z. So when we differentiate that f of z, we get f dash of z equal to minus sin z. So differentiating second time, we will get f double dash of z equal to minus cos z. So next time we will get f triple dash of z equal to sin z. By the same way, we need to integral f of pi by 2. So f of pi by 2 equal to 0. When we differentiate that, f dash of pi by 2 equal to minus 1 and f double dash of pi by 2 equal to 0 and f 4 dash of pi by 2 equal to 1. So by substituting these all in the above equation, we get the Taylor series of f of z about z equal to pi by 2. That is cos z equal to minus z minus pi by 2 divided by 1 factorial plus z minus pi by 2 into 3 the whole cube divided by 3 factorial minus z minus pi by 2 power 5 divided by 5 factorial plus etc. This expansion will be valid throughout the complex plane. So next see our another one question. So what is the question? Expand f of z equal to z minus 1 divided by z plus 1 as a Taylor series. And the first subdivision is about the point z equal to 0. Second subdivision is about the point z equal to 1. Determine the region of convergence in each case. So first let us consider first subdivision f of z. Let us consider f of z equal to z minus 1 divided by z plus 1. That is z minus 1 into 1 plus z the whole inverse. So we know the formula that 1 plus for for 1 plus z the whole inverse. So we will get z minus 1 into 1 minus z plus z square minus z cube plus etc. And if modulus z is less than 1. By expanding this form, we will get minus 1 plus 2z minus 2z square plus 2z cube plus etc. This region of convergence is modulus z is less than 1. Then and the neighborhood of 0 and 1 which are analytic are modulus z is less than 1 and modulus z minus 1 is less than 2. Because z minus 1 divided by z plus 1 is not analytic at z minus 1. Next, let us see the second subdivision. F of z equal to z minus 1 divided by z plus 1. Second subdivision is for the point z equal to 1. So, we get z minus 1 divided by 2 plus z minus 1. By adding and subtracting 2, we will get that. So, next, taking 2 common in denominator, we get z minus 1 divided by 2 into 1 plus z minus 1 divided by 2. Equal to taking that as common, we will get z minus 1 divided by 2 into 1 plus z minus 1 divided by 2 the whole inverse. We know the formula for 1 plus z minus 1 divided by 2 the whole inverse. By substituting the formula, we will get z minus 1 by 2 into 1 minus z minus 1 by 2 by plus z minus 1 by 2 the whole square minus z minus 1 by 2 the whole cube etc. So by reducing these, we will get equal to z minus 1 by 2 minus z minus 1 the whole square divided by 2 square plus z minus 1 the whole cube divided by 2 cube, etc. This region is convergence is given by modulus z minus 1 divided by 2 less than 1. Thank you.